Okay, we're recording again. This is part 2 of 7.1. Okay, now imagine taking a simple random sample of 50 M&Ms, make a graph showing a possible distribution of the sample data. Give the value and the appropriate statistics for this example, or this sample. Okay, let's go back over here and look at number 2. So they just did an imaginary sample. So this sample, there are 11 orange M&Ms. So p hat would be 11 out of 50, or 2.22, or 22%, okay? Now, if we look at their distribution, so here is their graph. It doesn't necessarily match the original one, but this is the one for that particular sample. All right, and then finally 3, which of the graphs that follow could be the approximate sampling distribution of the statistic? Explain your choice. All right, let's look at their answer. Oh, we have to look at those graphs. I'm sorry. Let's look at the graphs because it's on the next page. They're on the top of the next page. Okay, so the first one, they're asking which of the graphs could followed could be the approximate. Now notice when they say approximate, it's not the whole sampling distribution. It's approximate sampling distribution of the statistic. Would it be this one? The color? No, the color is just the distribution of the population of that sample. It's not a sampling distribution, right? It's not where you're taking samples and finding, you know, how many are orange, how many are orange, how many are orange several times. This is of one sample, right? And the orange was, there was 11 in that sample. Now, this one, what's the difference between this one and this one? Can you guys tell? I can make it bigger, maybe. And focus it. What? Okay, can you tell the difference between this graph and this graph?
It's distributed more. The second one.
The second one is what?
Distributed more than the...
What do you mean by that?
The dots are more spread out, I guess.
Okay, so it has a wider range?
Yeah.
Okay,
And
but let's look at the mean, or the proportion that we should be getting for orange.
Okay.
Orange, I can't think of the word. M&Ms. Thanks. Okay, which one is closest to the actual size for orange that it should be, the proportion?
The second one.
This one?
No, like
The second one.
that one.
Oh, second in the list. Yeah. Okay, so yes, they have the most should happen right there. So the median or the mean should happen right here where their proportion equals 0.2 if M&M's company, Mars company, is telling you the truth, right? Over here, if this were the case, then it would be a bias situation. Something is amuck. Okay. All right, now I'm going to try to get back on track here with my camera. Okay. Now we're going to talk about a biased and unbiased estimator. And I'm sorry I'm not doing this with my slideshow, but I've got to download the information on my computer. I mean the program, so I can actually do it. Let's see. Oh, no. It's doing something crazy. Getting used to this, folks. I'm getting used to it. Okay, that'll be good enough, I think. Okay, so now we're talking about an unbiased estimator. Let's return to the familiar chips example. How well does the sample proportion of red chips estimate the population proportion of red chips? Well, of P equals 0.5. So we're talking about the chips that we were drawing from, the red and blue, or the red and not red. The dot plot in the margin shows the approximate sampling distribution of p hat once again. So that's right here. It looks like lines, but there's many, many dots. We noted earlier that the center of the distribution is very close to 0.5. So this would be what we call an unbiased estimator. It's going to match up pretty close, maybe not exact, but really close to what the proportion should be. Okay, we noted earlier that the center of the distribution is very close to 0.5, the parameter value. In fact, if we took all possible samples of 20 chips, that would be the actual sampling distribution from the population, calculated p-hat for each sample, and then found the mean of all the p-hat values, we would get exactly 0.5. For this reason, we say that p-hat is an unbiased estimator of p. So here is a definition of an unbiased estimator. It is a statistic used to estimate parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. Okay, if they are very close or real. But in the teaching tip over here to the side, it is stating that to make sure to tell the students that unbiased doesn't mean perfect. An unbiased estimator will almost always provide an estimate that is not equal to the value of the population parameter. It is called unbiased because the repeated samples, the estimates won't consistently be too high or consistently be too low. Okay, now let's go to the next página, which we have not had a chance to do this activity yet either, but this activity is talking about taking the height of the people in the classroom and putting all of the values, and that is if you had 25 students in your class, because you could use, you have more information to work with. Now, and then having each one of the students take out a sample, like write them all on a piece of paper and put them in a bag, and then, so Dahana would, if she was the first person to do it, she would reach in the bag and draw 4 pieces of paper out, and with their initials on it and their height. Now, then she would write those down, put them back in the bag, and pass them on to Seth, and so on down the road. Okay, so everybody would have a sample of 4, right? And then each person would take their sample and find the mean height in inches, and then find their range in inches, okay? So, if we did that several times, this is what would happen. This is what happened with a specific class. Mrs. Washington's class did this sampling of the heights activity. They produced the 3 graphs shown in figure 7.4, and that's here, right here. Her students concluded that the sample mean x bar is probably an unbiased estimator of the population mean mu. Their reason, the center of the approximate sampling distribution, the approximate, notice it's not all of the possibilities, of x bar, is 65.67, which is very close to the population mean. If you took everybody's, found the actual mean, it's 66.07. Now, and we'll talk about on the other hand in just a second. So, if we have, this is the distribution of the population of the whole class. So there's somebody that's kind of vertically challenged. There's some people not so vertically challenged. They're horizontally challenged, apparently. Well, they may not be. I don't know. Anyway, so here's the distribution. Now, when we take samples of those, regardless of how wide this spread is, if we take samples of those and find their average, it's not going to be so widely spread, because every time you're getting an average, so it's going to move closer and closer and closer into the middle, right? That's why. So when they found what the average was using all of these means, they took all of those and then found that average. That would be 65.67. And then over here, we have got this approximate sampling distribution of the range, right? Because way back up here, they not only found the mean of their sample, but they found the range of their sample. Now, this is interesting. So if we look at this, the center mean is 10.12 inches. So, but what is the actual mean? Well, the actual mean would be going over here and taking the highest minus the lowest, and it tells us on the next page that this actual highest minus the actual lowest, so 75 minus 54, is 21 inches. So is the mean range very close to or similar to 21 inches?
Not really.
No, it's not. So which one of these, the approximate sampling distribution of the mean or the approximate sampling distribution of the range is unbiased?
Approximate sampling distributions of the mean.
Yes, this is the unbiased one because they match up pretty good. So this in turn would be
The biased one.
the biased one. They do not match up well. Okay, good. Now let's go to the next pagina. Whoa. Okay. Now, we already talked about that. That's the biased estimator is the range. Now, to confirm the class's conclusion, they used Fathom software to simulate taking 250 simple random samples of size 4 students. So 250 of those. We do not have time to do that. That's why they use the simulation on the software program. For each sample, we plotted the sample mean height x bar and the range of the heights in the sample. Okay, so here's our figure, and it shows us what they got. So the population distribution of the height, again, this is what we had on the last page. Now, this is the approximate sampling distribution of the 250 samples. Somebody's phone is ringing in the hallway. And somebody, oh no, somebody just answered it. Okay. Now, this is the approximate sampling distribution of the range. So they did lots of them to make sure that they were still correct. Do you feel like they were still correct? Okay, so before they got the center mean of the range, with just the 25 students doing it, they got 10.12 inches. Here, with 250 of those samples finding the range, they got 10.21 inches. So that they were not far off, right?
Yeah.
It's very, very close to that. However, it is not very close to the actual range, right? Which is 21. So still, this one is biased, this one is unbiased. And it gets really, really shows you the distribution here, and it is centered at the same spot, and so on. Okay, now, I'm not going to take a lot of time right here to explain. You can do the reading. Please don't forget to do your reading. I want you to read all of this. Just listening to me chatter away about it is not enough. Okay, but this tells you why, when we find this variance, why we divide by n minus 1 and not just n. And even though the sampling variance is an unbiased estimator of the population variance, when we use n minus 1 in the denominator, the sample standard deviation with the denominator n minus 1 is still a biased estimator of the true standard deviation. Okay, so you need to understand that when we use n minus 1, it helps it to be unbiased. Okay, you can read in here and understand that more. You're not going to have to explain that on the exam. But sometimes kids go, I don't understand why, when we find averages growing, when you're in smaller grades, we just divide by how many things there are. Yes, but you're not also doing variance and standard deviation. And so that helps us on that. Okay, but I don't have a lot of time to spend on that right now. Okay, so let's go down here to who watches Survivor. I think I have seen that a little bit in my life. I don't know what time it is. 1:12. Okay. Now, so television executives and companies who advertise on TV are interested in how many viewers are watching a particular show. Otherwise, they're not going to want to spend the money on that advertising, right? They're going to spend the money where it's going to help. Now, according to the Nielsen rating, Survivor was, I don't know if it still is or not, one of the most watched television shows in the United States during every week that it aired. Suppose that the true proportion of U.S. adults who have watched Survivor, if that is the true proportion, 0.37, figure 7.7, this is right here, shows the results of drawing 1,000 simple random samples of 100. So here, this is the results with all these proportions of 1,000 samples, but each one of these are out of 100 people. Okay? And then, from a population of, so the proportion, the actual proportion is still 0.37. We see that a sample of 100 people often gave a p-hat quite far from the population parameter. So do you see that here's the population parameter, 0.37, so that's still lovely. I don't know if you can tell what that says right there. Okay, well, this says 0.37 right here. So yes, it's centered on it. However, we have many that aren't. They're far away, right? But if we make that sample size much larger, 1,000, each one of them being 1,000, we're going to narrow it down. It looks like the Leaning Tower. Well, not so much leaning, but a tower of something. Maybe the Eiffel Tower. Okay, see, it's still centered around 0.37, but the range is much less distributed, like you were saying. The range is much smaller. So we're going to get more and more, because the greater the sample, the closer that is going to become toward the actual proportion. Okay? Okay, so now let me read the rest of them while you're still looking at that graph. That is why a Gallup poll asked not 100 but 1,000 whether they had watched Survivor. Let's repeat our simulation, this time taking 1,000, size and 1,000, which is what we already talked about right here. Okay, we can see that the spread of figure 77B or 7.7B, this red one, is much less than that of figure 7.7A. So the spread is much more narrow than here. Now, with samples of size 100, the values of p-hat can vary from 0.22 to 0.535, so quite a distance. The standard deviation of the p-hat values in the A, or the green one, is about 0.05. Using the simple random samples of size 1,000, the values of p-hat only vary from 0.32 to 0.42, so much smaller variation. The red one, the standard deviation is about 0.016, so much smaller standard deviation. Most random samples of size 1,000 people of p-hat are within 0.03 of the actual population parameter of 0.37. So most lie very close, where here you have a lot going out. Okay, now we're going to talk about variability in the statistics. So let's go to the next pagina, and here we go. The variability of a statistic. The variability of a statistic is decreased by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. Larger samples give smaller spread. That makes sense from what we just talked about. So, and by the way, if you sample everyone, you're going to be straight up right on the money, 0.37, right? But is that realistic? No, it's going to get in the way of time, it's going to get in the way of cost, or those things are going to get in the way of that. Okay, the spread of the sampling distribution does not depend on the size of the population, as long as the population is at least 10 times larger than the sample. Okay, why does the size of the population have little influence on the behavior of the statistics of the random samples? Notice when we did, well, they changed their size to 1,000, but the center was still at 0.37, right? And notice on, back here on this other page, well, that's not it. If you could look up just a little. Remember, we took all of these tons, like they did 250. Oh, I'm running.